Hello friends, in this video we will discuss solution of homogeneous linear partial differential equation with constant coefficient. So first we discuss linear partial differential equation. As we know, partial differential equation will be linear if the power of dependent variable is 1. Here z is dependent variable and x and y are independent variable. So in given equation the power of z must be 1, and also the power of derivatives of dependent variable should be 1. Whichever order of derivative is exist, its index must be 1. And third one, the product of dependent variable and their derivative should not exist in given equation. If all these conditions are satisfied, we say given equation is a linear differential equation. A general linear partial differential equation is given by here in equation number 1. This is an nth order linear partial differential equation. These are the terms of nth order. A naught del n z upon del x raised to power n, a1 del n z upon del x n minus 1 del y, and so on, an del n z upon del y n. These all are nth order terms. And b0 del n minus 1 z upon del x n minus 1, b1 del n minus 1 z upon del x n minus 2 del y, and so on, bn minus 1 del n minus 1 z upon del y n minus 1. These are the terms of n minus 1th order, plus so on, m0 del z upon del x, m1 del z upon del y, first order derivatives term, n naught z is equals to function of xy. Here the coefficient a0, a1, an, b0, b1, bn minus 1, m, n, these are either constant or some function of x and y, not a function of z. Either function of x and y or constant. If they a, b, m, n are constant, then we say these are linear partial differential equation with constant coefficient, otherwise with variable coefficient. So in this video we will discuss only those equations which are with constant coefficient, and right hand part is fxy, which is function of x and y. Further we look when a linear partial differential equation is homogeneous or when it would be non-homogeneous. So when all the derivatives appearing in one are of same order, then the resulting equation is called linear homogeneous partial differential equation. That is, in equation 1, which is this is equation number 1, we can rewrite it as in this form also by replacing del y del x with capital D and del y del y with capital D prime. So the equation 2 is same as equation 1. So if all the terms of given equation are of same order, then we say given equation is homogeneous. Means if given equation is nth order homogeneous equation, means it contains only the terms of nth order. If given equation is of first order homogeneous, then it contains only the terms of first order derivatives. So a homogeneous linear partial differential equation contains all the derivatives of same order. Otherwise it will be a non-homogeneous partial differential equation. It means order of derivatives are different or not same. Then it will be non-homogeneous partial differential equation with constant coefficient. Now I will discuss solution of linear homogeneous partial differential equation. Suppose we have a linear partial differential equation in nth degree, means nth order homogeneous. Its solution consists of two parts, CF and PI. First we look how to find complementary function. Complementary function solution of its auxiliary solution of the given equation when right hand part is 0. When right hand part is 0. So how we find CF? So before finding CF, we will write auxiliary equation of given differential equation. So for writing auxiliary equation, first we replace d with small m and d prime with 1 only. So what we get? We get a naught m raised to power n plus a1 m raised to power n minus 1, and in place of d prime we write 1, so it becomes a1 d raised to power m raised to power n minus 1. Further, plus a2 m raised to power n minus 2, and so on, an equals to 0. So this is an auxiliary equation about given equation. And now we will find the roots of this equation. This is an nth order equation, so it have n roots. Say m1, m2, mn are n roots of equation 2. Now we will discuss some case. If all these m, m1, m2, mn are distinct, then CF is equals to phi 1 y plus m1x plus phi 2 y plus m2x plus so on phi n y plus mnx. Here phi 1, phi 2, phi n are arbitrary function. So these are n arbitrary function. Now suppose if roots are repeated, if all roots are same, in that case m1 equals to m2 equals to mn. Suppose these all are equals to m. So CF is phi 1 y plus mx plus x time phi 2 y plus mx plus x square phi 3 y plus mx, and so on, x is to power n minus 1 phi n y plus mx. Now third case, corresponding to non-repeating factor d. In that case, when d is a factor of given equation, it means m is equals to 0 will be a solution of auxiliary equation. D is a factor, it means m is equals to 0 is a solution of auxiliary equation. So when we put the value of m in some phi is equal to phi into y plus mx, so it gives only phi of y. So the part of complementary function is phi of y, function of y. Here phi is arbitrary function. And if d is a repeated factor, about repeated factor of d, CF will be just like second case, phi 1y plus x phi 2y plus x square phi 3y, and so on, x is to power n minus 1 phi n y. Just in second case replace m is equals to 0, we get this case. Now further, corresponding to non-repeating factor d prime, in that case our order of auxiliary equation is of n minus 1th only. It means this is an equation of n minus 1th order which gives us n minus 1 root. But actually the given problem is nth order, so there should be n arbitrary function. So n minus 1 roots we can find here, and nth arbitrary function we will write about d prime. So when about non-repeating factor of d prime, we can write part of complementary function is phi x. In that case, if non-repeating factor of d prime exists, phi x is a part of complementary function. And if there are r factor of d prime, repeated factor, then CF will be about d prime r times phi 1x plus y phi 2x plus so on phi y raised to power r minus 1 phi r x. It means if there is a d prime factor in given equation, phi x is a part of complementary function, and if d prime is a repeated factor, then phi 1x plus y times phi 2x and so on, y raised to power r minus 1 phi r x r part of complementary function. So in this way we can find the complementary function for given equation. There is some alternate approach also. If the given equation which is f d d prime can be factorized, if given equation can be factorized, then about the factor bd minus ad prime, suppose bd minus ad prime is a factor of given equation, then about this factor we can directly write complementary function which is phi of by plus ax. Just by plus ax become a complementary function, a part of complementary function about the factor bd minus ad prime. And if bd minus ad prime are a repeated factor, suppose m times repeated, then the CF will be phi 1 by plus ax plus x times phi 2 by plus ax plus so on x raised to power m minus 1 phi m by plus ax. So this we can use this approach also and the previous approach. Now we will use some notation. As we know, if z is a function of x and y, z is dependent variable, x and y are independent variable, then del z upon del x represented by small p. Similarly, small q represent del z upon del y. And now we introduce some more standard notation. R, s and t. Small r represent del 2z upon del x square. It means second order partial derivative of z with respect to x. S represent second order partial derivative of z with respect to x and y, del 2z upon del x del y. Similarly, t is del 2z upon del y square. These are some standard notation we will use. So let's try some problem. R is equals to a square t. First we are to write it into standard form, that is f d d prime equals to some function of xy. So we replace a square t into left hand part, it becomes r minus a square t. Here right hand part is 0. So its solution, complementary function is the complete solution. Z is equals to CF is only solution. The PI of given equation is 0. Or we can rewrite it as del 2z upon del x square minus a square del 2z upon del y square, as r is del 2z upon del x square and t is del 2z upon del y square. Taking del z upon del x is d and del z upon del y is d prime, we can rewrite given equation as d square minus a square d prime square equals to 0. This is square of d prime, not whole square. So we can write it as like this, equals to 0. Now we factorize it, we get d minus ad prime and d plus ad prime equals to 0. So using alternate approach, its CF should be in, this is what, bd minus ad prime. So b is 1 and a is a, so it becomes y plus ax, y minus ax. So its CF is z is equals to phi 1 y plus ax plus phi 2 y minus ax. This we compare this vector with bd minus ad prime. Bd, value of b is 1 minus ad prime, a is a, so y by plus ax. So in place of b we will put a and in place of a we will put a, so it becomes phi 1 y plus ax. Here b is 1 and a is minus a, so it becomes phi 2 y minus ax. Or we can write its auxiliary equation. By auxiliary equation we can write its complementary function. So auxiliary equation of given problem is m square minus a square equals to 0. It gives us 2 root m is equals to plus minus a. So about both are distinct. So about a and minus a, CF is phi 1 y plus ax plus phi 2 y minus ax. So both are same. Hence its solution will be z is equals to CF, that is z is equals to phi 1 y plus ax plus phi 2 y minus ax, here x. This is complete solution or general solution of given problem, as pi is 0 here. Let's take another problem. D cube minus 6d square d prime plus 11d d prime square minus 6d prime cube z equals to 0. We write its auxiliary equation. To write its auxiliary equation, just replace d with m and d prime with 1. So it becomes m cube minus 6m square plus 11m minus 6 equals to 0. Now this is an equation of third degree. It has 3 roots. So first we satisfy it, m is equals to 1. So m equals to 1 satisfy this equation, so m minus 1 must be a factor of this equation. To find another 2 factor, we divide this term m cube minus 6m square plus 11 minus 6 by m minus 1 in this way. When we divide it, we get m square minus 5m plus 6. This is 6. This is another factor. So we can factorize it m minus 1, m square minus 5m plus 6. Or we can factorize it as m minus 1, m minus 2, m minus 3 equals to 0. Hence m is equals to 1, 2, 3 are 3 roots of this auxiliary equation. So about these 3 non-repeated roots, complementary function can be written as phi 1 y plus x about m is equals to 1. About m equals to 2, it will be phi 2 y plus 2x, and about m equals to 3, it will be y plus 3x, phi 3 y plus 3x, and z is equals to CF is complete solution. Let's try another problem. D cube minus 3d square d prime plus 2d d prime square equals to 0. Its auxiliary equation is m cube minus 3m square plus 2m. When we taking m outside, it becomes m into m square minus 3m plus 2 equals to 0. It will be m minus 2, m minus 1. These are factor of given auxiliary equation. So m is equals to 0, 1 and 2 are roots of auxiliary equation, and about 0, 1 and 2, the complementary function is phi 1 y taking m is equals to 0, and when m is equals to 1, it becomes phi 2 y plus x, and for m is equals to 2, it becomes phi 3 y plus 2x. This is the case when d is a factor, d is a non-repeated factor of given equation. Taking d outside, it becomes third case. We discussed earlier here, corresponding to a non-repeating factor d. In that case, m is equals to 0 is a root of auxiliary equation. So this is same as here. Let's take another problem. It's d4 plus d prime square minus 2d square d prime square. Its auxiliary equation is m raised to power 4 plus 1 minus 2m square, or we can write it as m raised to power 4 minus 2m square plus 1 equals to 0, and this is what m square minus 1 whole square equals to 0, and the factor of m square minus 1 is m plus 1, m minus 1. So m plus 1 is a 2 times repeated factor, m minus 1 is also a 2 times repeated factor. So the roots of this auxiliary equations are 1, 1, minus 1 and minus 1. So about 1 and 1, CF, part of CF is phi 1 y plus x plus x, phi 2 y plus x. And about the repeated factor minus 1, the part of CF is phi 3 y minus x plus x, phi 4 y minus x. And z is equals to CF is complete solution. So this is complete solution of given problem. Let's take one more problem. d cube d prime minus 4d square d prime square plus 4d d prime cube z is equals to 0. Or we can write it as d prime d minus 2d prime whole square equals to 0. First we write its auxiliary equation m cube minus 4m square plus 4m equals to 0, or m into m square minus 4m square plus 4 is equals to 0. This is 4m only, not square, because taking m outside, here the remaining term is m square and here remaining term is m, and here without m. So m square minus 4m plus 4 into m, these are two factors of this equation. Or we can write it as m into m minus 2 whole square equals to 0. And root of this auxiliary equation are 0, 2 and 2. 2 is a repeated factor. So about 0 part of CF is phi 1 y, and about 2 and 2 part of CF is phi 3 y plus 2x and x phi 4 y plus 2x. But the given equation is of fourth order homogeneous partial differential equation, so there should be 4 arbitrary function, but from here we can write only 3 arbitrary function. So when we write it as in this form, we look here, d prime is a factor, d prime is also a factor of this equation, and about d prime we can write phi 1 x is a part of CF. So when we write it in this form, about d prime we write phi 1 x is a part of CF. It means whenever the order of auxiliary equation is reduced by order of actual differential equation, then there should be some term of phi 1 x type appear in complementary function, and number of terms are equals to the prime the factor d prime repeated how many times it appear, phi 1 x appear in those number of terms in complementary function. So z is equals to phi 1 x, the phi 1 x is about d prime, and phi 2 y, this is about d, plus phi 3 y plus 2x, and x phi 4 y plus 2x, this is about d minus 2d prime square. This is complete solution. And let's take one more problem. d4 minus d prime 4. Here auxiliary equation is m raised to power 4 minus 1 is equals to 0, or we can write it as m square minus 1 m square plus 1. When we further factorize it, we get m plus 1 m minus 1 from first factor, and from second m square plus 1 we get m plus iota minus iota. Here some complex roots appear, but CF is as usual phi 1 y plus x about m is equals to minus 1, sorry about m is equals to 1 from here, and about m is equals to minus 1 phi 2 y minus x, about m is equals to iota phi 3 y plus iota x, and about m is equals to minus iota phi 4 y minus iota x, and z is equals to CF is complete solution. So this is about how we are to find complementary function of given homogeneous linear partial differential equation. Thank you.